This is the 4.1 to 4.2 review. Calculators are not allowed, and our goal is to find the absolute extreme values on these piecewise functions in disguise. So this is a lot like the one that we did in class, example 1, part D, I think, in section 4.1 of skill 2 and 3. So we're going to have to figure out what the pieces are for this, and then find the absolute maxes and mins. So part A, if we look at it, I see that I have a domain of all reals because there's no division, there's no square roots, there's no logs. And now for my second step, I need to take the derivative. Well, I can't take the derivative of this until I get rid of the absolute values. So looking at this original problem, we can see that the behavior of this absolute value will change at 2, and the behavior of this absolute value will change at -3. So I'm going to split my domain into 3 components. I'll have an issue at -3 and at +2. So I'm going to be changing behavior around those corners. So first let's pick a number that's less than -3, say -4. This will be a negative number, so that means the absolute value will take its opposite. If I am still smaller than -3 and I plug into here, that too will be a negative number, so the absolute value will change its sign. If I simplify that, I have a -x plus a -x gives me a -2x, and then I have a +2 minus a 3 gives me a -1. Now if I look at the next section between -3 and 2, say it's 0, plug that in, I have a negative number again, so I will take the opposite, plus plug in 0 here, this time it's positive, so the absolute value will leave that x plus 3 alone. Put these together, I have a -x plus an x, that's going to have no x's, and a +2 plus a 3 gives me a 5. Okay, the third branch is when I'm larger than 2, so say 7, plug that in, this will be a positive number, so the absolute value will leave it alone, and this 2 will be a positive number, so I will leave it alone. Add up, I get a 2x minus a 2 plus a 3 is plus a 1. Okay, so we are on this branch for all x's less than or equal to -3. We're on this branch for things between -3 and 2. And we are on this branch for x's greater than or equal to 2. So now, we're only at step 2 in the process. Step 3, 4, 5 would require us to take the derivative, identify the critical points, then sketch f prime, then from that sketch f. And that will generate a graph from which we can identify the maxes and mins. So rather than doing that, I'm going to actually sketch this graph because this one's pretty easy to see. So we don't need to go through all the other processes just to figure out what the graph is, because we can graph it as is since the pieces are all linear. If I look at what I have here, I'm on the line 2x minus 1 as long as x is less than -3. So what I'm going to do is I'm going to plug in -3 to see what comes out. If I plug in -3, I get a 6 minus a 1 is a 5. 1, 2, 3, 4, 5. Prior to that, I'm on a line that has a slope of -2. Then between -3 and +2, I'm on a line whose y-coordinate is always 5. So from -3 until 2, I'm on this line 5. Then the last piece, again, if I plug in the joint, which is 2, I'm going to get that 5. I'm going to connect here, and then I'm going to have a slope of +2. Now, backtracking up to the beginning, I wrote the domain was all reals, and that was a lie because I neglected this. I'm actually restricted by the problem itself, so I'm only going to be able to look from -6 to +5. So if I plug in a -6, into this branch, I get a 12 minus 1 gives me 11. So I've got the point -6, 11. Then I've got the point -3, 5. Then I've got 2, 5. And then I'm also going to plug in a 5. 1, 2, 3, 4, 5. If I plug in 5 on this branch, it's a 10 plus 1 is an 11. So we're going to ignore these pieces because we don't get to go past the domain. Looking at this picture now, we can see that there's a minimum value of 5 on this entire interval from -3 to 2, and we have a maximum value of 11 that occurs in 2 places. So we can write down that we have a min of 5 on the interval from -3 to 2, and we have a max of 11 at x equals -6 and +5. So let's do that same process with b, and this time I won't ignore the given domain. So scoot this up, I'll write down b, and then we can scoot so we can see more. So for b, we have f of x equals absolute value of x plus 4 minus absolute value of x minus 4, and we're on the interval from -2 to 7. So my domain in this problem will be all reals between -2 and 7. And we need to pay attention to when the behavior of this function is going to change. So it will change at -4 and again at +4. So on this number line, we will put our -2 and 7 on there, and we're going to change at -4, which is off the picture, and then at +4, we're going to have a change. So really, this function on this domain will only have 2 pieces because it won't change until outside of the domain. So that means we're going to have a piece that starts from -2 to 4, and in between -2 and 4, say it's 0. This is positive, so it's left alone, and this is negative, so we're going to change its sign. Simplify, we get an x plus an x. We have a 4 minus a 4. This is the case whenever we're between -2 and 4. For this branch between 4 and 7, say at 5, this will be positive and this will be positive. So those absolute values will leave both of them alone. If we look carefully, we'll have an x minus an x, they disappear, and a 4 plus a 4 will give me an 8. So again, just like we did in part A, we can graph this function already because it's just piecewise from -2 to 4. We are on the line, oops, excuse me, 2x. So at -2, if I plug that in, I get a -4. And at +4, I plug it in and I get an 8. Then after that, from 4 to 7, notice I can use the equal sign in either place. It doesn't matter because they connect. I will be at 8. 1, 2, 3, 4, 5, 6, 7. So here's our picture of our function. So based on this picture, we can see that the minimum is down here at -2, -4, and the max is up here at 8 all along the interval. So we would write, we have a min of -4 at x equals -2, and we have a max of 8 on the entire interval from 4 to 7.